morning, everyone. My name is Kai Wen, and we're presenting our system role-playing hallucination, or in short, RPLH, a lightweighted system for collaboration framework. And I'm here with my teammates. And so, why multi-agent? I just want to give a quick thing because multi-agents, people sometimes say that it's like, why use more agent when you can use one? But sometimes we have partial observation, partial action. Each agent is limited to themselves. So we need more people to do tasks together to solve some complicated task. And I just want to remind everyone that it can still be framed as an MVP, which I'm not going to go specifically into it, but it's essentially a hard problem that we need to solve.
Literature review and then collaboration. So the first thing I want to mention is collaboration. So there's a previous research project about Koala, which build an embodied like multi-agent system in the embodied environment. The second one is more communication. There's another paper about the communication about multi-agency, which tells different communication framework for multi-agent systems. That's where our motivation comes from. And what's the problem and the motivation? So the first, in context learning and chain of thought. So for prompting, if we ask the agent to give the reasons during the answering the questions, it will increase the accuracy dramatically. From another perspective, agent-based reasoning. Their researchers propose this framework that helps the agent build internal belief during completing the tasks.
Okay, so what makes now difference? We have large language model, but what makes us different is that we are a lightweight system. We can run on a MacBook. All training is run on my MacBook. So no computation, super high computation costs or API costs. So we use lightweight system with QN, 14 billion parameters, and then some little engineering tricks with fine state machines for ensuring syntactic correctness. And then we have a hallucination system in such that each agent is trying to reason from other agents' perspective, and then in the essence, trying to complete the collaboration task. And then, so this is hallucination. So what's the system? It's engineering, and some optimization tricks. So no training, no retraining, everything is an inference time. It's an inference system. And quick overview of our structure is we have an agent doing stuff, we have a hallucination central agent, and then we have an information constant, which is how we gather data flow, and we have a judge, and the interaction with the environment. The key thing is the data flow, which I'll go into a little bit later. But the environment here, we're using a simple task environment, which is agent trying to move boxes around. And each agent can only see the two grids next to it. So there's the partial information and then partial action that agent can do. So data flow is extremely the key. I'm not going to go into it, but essentially we made some formulation of what governs the information flows in our system and how we're going to use it. And let's run through a quick example of our algorithm, which is each agent try to hallucinate themselves. That's the HCA agent, and then they try to reason what other agents are doing based on something we call attitudes. And then there's some optimization tricks, and then attitudes agents would judge attitude and pass only attitudes around to the next iteration. This is trying to keep data flow the minimal, and then because our language model doesn't respond well to a lot of prompts. So we try to minimize the prompt as well. And then the judge will make final decision, which gives us what they think is the optimal action.
So the LM prompt is the backbone of our system. So here we're showing examples of the central agent prompt. We structure our prompts into categories such as as we can see, the agent identification information, the environment description, we have the current state, the agent characteristics, and we also see an example of the LM response, the structure as the attitude, the chain of thought learning. They also give the action plans. We also implement a action checker to ensure that the input to the environment is correct. And our major contribution, we develop a lightweight multi-agent collaboration systems using local LMs. And the key points of our system is the data flow information. We believe this is how the intelligence emerges. And another key point is the agent-based reasonings. Each agent in our environments think, communicates, and interacts individually. And this is from our entire multi-collaboration systems. And we are going to, in the future, we are going to do more evaluations comparing the basic centralized and decentralized system using measures such as the average number of success, the accuracy, the success rate, the average number of API calls, and the number of execution steps. And right here, we are going to show you a quick demos about our systems very successfully completing the test. The environment is set to match the color deep box to the targets. And yeah, and that's all.
Yes.
And we open to any question and comments.
So we made this websites for all documentations of our system, and feel free to give any comments if you guys want to run the code yourself.
Okay, great. Questions? Could you probably explain this demo a little bit?
So the circles are the targets and the diamonds are the boxes, and we are trying to move the box to the right target. And so you can see they're eliminating each other at the robots at the large language model. And if you want to move a box to another grid, that's how you move the box. And why it's like blinking is a special event.
So
And it with every single box and target are limited each other, it will converge. Yes.
and each agent, let's say, if we're looking at this agent here, it can only move to this one and this one. So there is the partial action that is only doable for each agent.
Yes. Question? Okay. Yeah, great. Maybe in the final report you can discuss a bit more like how this could generalize to other settings.
Our next step is deploy this communication system into virtual home. And yeah.
We hope it will deploy to other settings, such as in multi-agent codings or like transportation problems. And we hope this system can scale to other environments.
Okay, sounds good.
One major challenge is where, since we have a lightweight system, so making sure that the agent is giving correct syntactic, correct outputs to other system has been a key challenge, but we're sort of doing a fine state machine tuning to make sure that it follows certain dictionary JSON format that it can actually run the system.
Great.